The authority having jurisdiction, or AHJ, indeed has a duty to enforce the correction of electrical deficiencies when the available fault current from a utility transformer exceeds the interrupting rating of the main circuit breaker within a facility. This responsibility stems from established electrical codes and standards, most notably the National Electrical Code, or NEC, which is also known as NFPA 70. NFPA 70, Section 110.10 is very clear on this subject. This section mandates that electrical equipment must be installed and used in accordance with the instructions included in the listing or labeling of the equipment. This requirement encompasses all electrical components, including transformers and circuit breakers, ensuring that they are selected and installed based on the manufacturer's specifications and limitations. When the available fault current surpasses the interrupting rating of the main circuit breaker, it constitutes a direct violation of NFPA 70, specifically Section 110.10. This violation creates a significant safety hazard, as the circuit breaker may not be able to safely interrupt the flow of current during a fault condition. The consequences of such a scenario can be severe, including equipment damage, fire, and potential injury or death to personnel. The AHJ role is to ensure that electrical installations comply with the NEC and other applicable codes and standards to safeguard people and property from electrical hazards. When the AHJ identifies a situation where the available fault current exceeds the circuit breaker's interrupting rating, they are obligated to take action to rectify the deficiency. The AHJ typically has the authority to issue notices of violation, require corrective action plans, and even shut down the electrical system if the hazard poses an imminent threat to safety. The building owner or facility operator is ultimately responsible for ensuring that the electrical system is safe and compliant with all applicable codes and standards. When notified of a deficiency by the AHJ, the owner must take prompt and effective steps to correct the problem. This may involve replacing the circuit breaker with one that has a higher interrupting rating, installing current limiting devices to reduce the available fault current, or making other modifications to the electrical system to bring it into compliance. In addressing this type of issue, it's important to understand the concepts of available fault current and interrupting rating. Available fault current refers to the maximum amount of current that an electrical system can deliver during a short circuit or ground fault condition. The magnitude of the available fault current depends on factors such as the size and impedance of the utility transformer, the impedance of the conductors, and the presence of any current limiting devices. The interrupting rating of a circuit breaker, on the other hand, is the maximum amount of fault current that the breaker can safely interrupt without being damaged or causing an arc flash. Circuit breakers are designed with specific interrupting ratings to protect the electrical system and personnel from the hazards of overcurrents. When selecting a circuit breaker, it is crucial to ensure that its interrupting rating is equal to or greater than the available fault current at the point of installation. Failure to do so can result in the circuit breaker failing to interrupt the fault current, leading to equipment damage, fire, and potential injury or death. Several methods can be employed to correct a situation where the available fault current exceeds the circuit breaker's interrupting rating. Firstly, replacing the existing circuit breaker with one that has a higher interrupting rating is a common solution. Circuit breakers are available with a range of interrupting ratings, and selecting a breaker with an appropriate rating for the specific application is essential. Secondly, installing current limiting devices, such as current limiting fuses or reactors, can reduce the available fault current to a level that is within the circuit breaker's interrupting rating. These devices work by increasing the impedance of the electrical circuit, thereby limiting the amount of current that can flow during a fault condition. Thirdly, modifying the electrical system to reduce the available fault current can also be an effective solution. This may involve increasing the size of the conductors, adding impedance to the circuit, or changing the configuration of the electrical system. It is crucial to consult with a qualified electrical engineer to determine the most appropriate solution for a given situation. A thorough fault current study should be conducted to determine the available fault current at various points in the electrical system. This study will help identify any locations where the available fault current exceeds the circuit breaker's interrupting rating and will provide the information needed to select appropriate corrective measures. The fault current study should be performed by a qualified electrical engineer using specialized software and techniques. The engineer will collect data on the electrical system, including the size and impedance of the utility transformer, the impedance of the conductors, and the characteristics of any current limiting devices. This data will be used to calculate the available fault current at various points in the system. Once the fault current study is complete, the engineer will prepare a report that summarizes the findings and recommendations. The report will identify any locations where the available fault current exceeds the circuit breaker's interrupting rating and will recommend appropriate corrective measures. The corrective measures may include replacing circuit breakers, installing current limiting devices, or modifying the electrical system. It is important to implement the recommendations of the fault current study to ensure the safety and reliability of the electrical system. In addition to the technical aspects of correcting a fault current deficiency, it is also important to consider the regulatory requirements. The AHJ will typically require the building owner to submit a corrective action plan that outlines the steps that will be taken to address the deficiency. The corrective action plan should include a timeline for completing the work and should identify the qualified electrical contractors or engineers who will be performing the work. The AHJ may also require the building owner to obtain permits and inspections to ensure that the work is performed in accordance with applicable codes and standards. It is important to work closely with the AHJ to ensure that all regulatory requirements are met. The AHJ is a valuable resource for information and guidance on electrical safety and compliance. They can provide assistance with interpreting codes and standards, reviewing corrective action plans, and conducting inspections. By working collaboratively with the AHJ, building owners can ensure that their electrical systems are safe and compliant. The NEC provides detailed requirements for overcurrent protection, including the selection and installation of circuit breakers. Article 240 of the NEC covers overcurrent protection in general, while Article 430 covers overcurrent protection for motors. These articles provide specific requirements for the interrupting rating of circuit breakers, as well as other important considerations such as the coordination of overcurrent protective devices. The NEC also contains tables and examples that can be used to calculate the available fault current at various points in the electrical system. These tables and examples can be helpful in selecting appropriate circuit breakers and other overcurrent protected devices. In addition to the NEC, other standards and guidelines may also be applicable. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards that provide guidance on fault current calculations and coordination of overcurrent protective devices. These standards can be valuable resources for electrical engineers and contractors. It is important to stay up to date on the latest codes, standards, and guidelines to ensure that electrical installations are safe and compliant. The electrical industry is constantly evolving, and new technologies and practices are being developed all the time. By staying informed, electrical professionals can provide their clients with the best possible service and ensure the safety of people and property. In summary, when the available fault current from a utility transformer exceeds the interrupting rating of the main circuit breaker, the AHJ has a duty to force the building owner to correct the deficiency. This duty is based on the NEC and other applicable codes and standards. The building owner is responsible for ensuring that the electrical system is safe and compliant and must take prompt and effective steps to correct any deficiencies identified by the AHJ. Corrective measures may include replacing circuit breakers, installing current limiting devices, or modifying the electrical system. A thorough fault current study should be conducted to determine the available fault current at various points in the electrical system. It is important to work closely with the AHJ to ensure that all regulatory requirements are met. By taking these steps, building owners can ensure that their electrical systems are safe and reliable. The role of the AHJ is paramount in ensuring electrical safety. They act as the primary enforcers of electrical codes and standards, safeguarding lives and property from potential hazards. Their responsibilities extend beyond simply identifying violations. They also play a crucial role in educating building owners, contractors, and the public about electrical safety best practices. This educational aspect helps prevent future violations and promotes a culture of safety within the electrical industry. Furthermore, the AHJ serves as a vital link between the technical requirements of electrical codes and the practical application of those requirements in the field. They interpret codes, resolve ambiguities, and provide guidance to ensure consistent and effective enforcement. Their expertise and experience are invaluable in navigating the complexities of electrical installations. The AHJ authority stems from their legal mandate to enforce electrical codes and standards. This authority empowers them to issue notices of violation, require corrective action plans, and, if necessary, shut down unsafe electrical systems. These powers are essential for ensuring compliance and protecting the public from electrical hazards. However, the AHJ role is not solely punitive. They also work collaboratively with building owners and contractors to achieve compliance. They provide technical assistance, review plans, and conduct inspections to help ensure that electrical installations meet the required safety standards. This collaborative approach fosters a positive working relationship and promotes a shared commitment to electrical safety. The importance of regular electrical inspections cannot be overstated. These inspections are a critical component of maintaining a safe and reliable electrical system. They allow the AHJ to identify potential hazards, verify compliance with codes and standards, and ensure that electrical equipment is properly installed and maintained. Regular inspections can also help prevent costly repairs and downtime by identifying problems before they escalate into major issues. Building owners should view electrical inspections not as a burden but as an investment in the safety and longevity of their electrical systems. By working proactively with the AHJ and scheduling regular inspections, they can minimize the risk of electrical hazards and ensure the continued safe operation of their facilities. The NEC is a comprehensive document that covers a wide range of electrical safety topics. It is updated every 3 years to reflect the latest technological advancements and best practices. Staying current with the NEC is essential for all electrical professionals, as it provides the foundation for safe and compliant electrical installations. The NEC is organized into chapters, articles, and sections, making it easy to find information on specific topics. It covers everything from wiring methods and overcurrent protection to grounding and bonding. It also includes detailed requirements for specific types of equipment and installations, such as motors, transformers, and hazardous locations. The NEC is not a static document. It is constantly evolving to address new challenges and improve electrical safety. The code-making process is open and transparent, allowing stakeholders from across the electrical industry to participate in the development of new requirements. This collaborative approach ensures that the NEC remains relevant and effective in protecting the public from electrical hazards. The application of electrical safety principles extends beyond traditional building settings. It is equally important in industrial facilities, healthcare facilities, and even residential homes. In each of these environments, electrical hazards can pose significant risks to people and property. Industrial facilities often have complex electrical systems that power heavy machinery and equipment. These systems require careful design, installation, and maintenance to ensure safety and reliability. Healthcare facilities rely on electricity to power life-saving medical equipment. Electrical outages or malfunctions can have serious consequences for patients. Residential homes also have potential electrical hazards, such as overloaded circuits, faulty wiring, and damaged appliances. By understanding the principles of electrical safety and taking appropriate precautions, individuals can minimize the risk of electrical accidents in their homes. Electrical safety is a shared responsibility. It requires the cooperation of building owners, contractors, electrical professionals, and the public. By working together, we can create a safer electrical environment for everyone. The AHJ plays a crucial role in this collaborative effort, providing guidance, enforcement, and education to ensure that electrical installations meet the required safety standards. The NEC serves as the foundation for electrical safety, providing detailed requirements for safe and compliant installations. By staying informed, following best practices, and working proactively with the AHJ, we can minimize the risk of electrical hazards and protect people and property from harm. The complexity of modern electrical systems demands a high level of expertise and attention to detail. Electrical professionals must possess a thorough understanding of electrical codes, standards, and best practices. They must also be able to apply this knowledge in practical situations, ensuring that electrical installations are safe, reliable, and compliant. Continuous training and education are essential for electrical professionals to stay current with the latest technological advancements and code changes. The electrical industry is constantly evolving, and new challenges and opportunities arise regularly. By investing in their professional development, electrical professionals can enhance their skills, improve their performance, and contribute to a safer electrical environment. The use of technology is also transforming the electrical industry. New tools and software are being developed to improve the efficiency and accuracy of electrical design, installation, and maintenance. For example, Building Information Modeling, or BIM, is being used to create virtual models of electrical systems, allowing engineers and contractors to visualize and coordinate their work more effectively. Thermal imaging is being used to detect hotspots in electrical equipment, allowing maintenance personnel to identify potential problems before they lead to failures. And smart meters are being used to monitor energy consumption and identify opportunities for energy savings. As technology continues to advance, it will play an increasingly important role in the electrical industry. Electrical professionals who embrace technology will be better equipped to meet the challenges of the future and provide their clients with the best possible service. The future of electrical safety depends on a continued commitment to education, innovation, and collaboration. By investing in these areas, we can create a safer and more sustainable electrical environment for generations to come. The AHJ will continue to play a vital role in this effort, providing guidance, enforcement, and education to ensure that electrical installations meet the required safety standards. The NEC will continue to serve as the foundation for electrical safety, providing detailed requirements for safe and compliant installations. And electrical professionals will continue to be the backbone of the electrical industry, providing the expertise and skills needed to design, install, and maintain safe and reliable electrical systems. Together, we can create a brighter and safer future for all. Available fault current calculations are a cornerstone of electrical system design and safety. These calculations determine the maximum current that can flow during a short circuit or ground fault, providing critical information for selecting appropriate overcurrent protection devices. The accuracy of these calculations is paramount, as an underestimation can lead to inadequate protection, while an overestimation can result in unnecessary expenses and system inefficiencies. Several methods exist for calculating available fault current, each with varying degrees of complexity and accuracy. Point-to-point calculations are a common approach, tracing the impedance of each component in the circuit from the source to the point of interest. This method requires detailed information about the transformer, conductors, and other devices in the system. Software-based calculations offer a more sophisticated approach, utilizing computer programs to model the electrical system and perform fault current calculations. These programs can handle complex systems with multiple sources and branches, providing more accurate results than manual calculations. Regardless of the method used, it is crucial to verify the accuracy of the calculations by comparing them to actual measurements or by using alternative calculation methods. Inaccurate fault current calculations can have serious consequences, so it is essential to ensure that the results are reliable. The coordination of overcurrent protective devices is another critical aspect of electrical system design. Coordination ensures that the protective devices closest to the fault will trip first, minimizing the impact of the fault on the rest of the system. This selective tripping prevents unnecessary outages and protects equipment from damage. Time current curves are used to visualize the tripping characteristics of overcurrent protective devices. These curves plot the tripping time of the device against the magnitude of the fault current. By comparing the time current curves of different protective devices, engineers can ensure that they are properly coordinated. Coordination studies are typically performed using specialized software that simulates fault conditions and analyzes the tripping characteristics of the protective devices. These studies can identify potential coordination problems and recommend adjustments to the device settings to ensure proper operation. The selection of overcurrent protective devices is based on several factors, including the available fault current, the load current, and the coordination requirements. Circuit breakers and fuses are the two primary types of overcurrent protective devices. Circuit breakers are reusable devices that can be reset after tripping, while fuses are single-use devices that must be replaced after tripping. The interrupting rating of the overcurrent protective device must be greater than or equal to the available fault current at the point of installation. This ensures that the device can safely interrupt the fault current without being damaged. The continuous current rating of the overcurrent protective device must be greater than or equal to the load current. This ensures that the device will not trip under normal operating conditions. The selection of overcurrent protective devices is a critical aspect of electrical system design, and it is essential to consult with a qualified electrical engineer to ensure that the devices are properly selected and coordinated. Grounding and bonding are essential for electrical safety. Grounding provides a low-impedance path for fault current to return to the source, allowing the overcurrent protective device to trip and clear the fault. Bonding connects all metal parts of the electrical system together, creating an equipotential plane that minimizes the risk of electric shock. The grounding electrode system consists of a grounding electrode, such as a ground rod or a metal water pipe, and a grounding electrode conductor that connects the electrode to the electrical system. The size of the grounding electrode conductor is based on the size of the service entrance conductors. The bonding system consists of bonding jumpers that connect all metal parts of the electrical system together, including metal conduits, metal enclosures, and metal equipment. The size of the bonding jumpers is based on the size of the circuit conductors. Proper grounding and bonding are essential for protecting people and equipment from electrical hazards. Regular inspections and testing are necessary to ensure that the grounding and bonding systems are functioning properly. Electrical safety is a continuous process that requires ongoing attention and effort. By following the principles of electrical safety, we can minimize the risk of electrical hazards and protect people and property from harm. The AHJ plays a crucial role in this process, providing guidance, enforcement, and education to ensure that electrical installations meet the required safety standards. The NEC serves as the foundation for electrical safety, providing detailed requirements for safe and compliant installations. And electrical professionals are the backbone of the electrical industry, providing the expertise and skills needed to design, install, and maintain safe and reliable electrical systems. Together, we can create a brighter and safer future for all.